We'll switch to the next talk. It will be a hybrid. Professor Mihai Gabriel will talk from Romania, and we'll have Dan here locally. And for all so after this session is over, we'll take the photo. All the online attendees, we are running around 10 to 12 minutes late. So we'll take the photo around 12:30. We'll take first the online picture, and then we'll go outside. So I think we are running around 10 to 15 minutes late. Okay. So we heard from Keysight people yesterday how they're trying to come up with their solutions to actually see how to estimate. Go back. I think there's no. Yeah. So today they will be talking like how they're trying to do predictive performance modeling and synthetic workload generation for the parallel DNN and LLM training. It will be presented by remotely Mihai Gabriel. He's a lecturer and researcher at the AI Multimedia Labs Campus Research Institute at the National University of Science and Technology in Bucharest, Romania. His research interests are focused on multimedia, multimodal data processing with neural networks, deep and ensemble learning, large language models and training process, description and optimization. And here we are joined in person by Dan Mihalescu. He's a senior software architect at Keysight, also based in Bucharest, but he flew here. He has extensive experience in building networking and security verification systems. So he leads the teams at Keysight Technologies Romania, focused on developing AI infrastructure emulation solutions and drives collaboration with academia and industry partners. So let's welcome both of them. And we can actually bring Mihai also on the screen, right? We should be able to see. Mihai, you can turn on your video. We can watch you. Yeah. Yes. Okay. Go ahead.
Hello, everyone. I'm Dan. I'm from Keysight Technologies, and together with Gabriel from University Polytechnica Bucharest, we'll present our work on performance prediction and synthetic chakra trace generation. Some of you may remember last year's MUG presentation when Winston and I introduced ML Commons chakra. And I'll begin with a short reminder of it before presenting the three research questions that we explored. Modern AI infrastructure is developed through a continuous hardware-software co-design cycle. We observe production workloads, we reproduce their behavior, we evaluate new designs, and eventually we end up deploying them at scale. But hardware cannot be optimized without understanding the workload, and the software cannot be optimized without understanding the hardware. The challenge is that real workloads evolve quickly and are very often proprietary. And the chakra's purpose is to provide the representative workload description that's needed to connect these two sites. So, chakra is an open graph-based representation of distributed AI workload behavior that covers compute, memory, communication, dependencies, and timing. A chakra execution trace is represented as a direct acyclic graph where nodes describe the operation and edges describe the data, the control, or the synchronization dependencies. It captures the information required for performance analysis without requiring access to model weights, dataset, or other proprietary source code. This makes chakra a common language between workload owners, hardware vendors, and simulation teams and researchers. Using chakra as our foundation, our collaboration focused on three questions. Can operation duration be predicted across different world sizes? Can valid chakra traces be generated without executing the workload? And can timing be extrapolated to unseen operation sizes on the same GPU? These questions led to our scaling prediction model, a synthetic chakra trace generator, and temporal prediction model. With that context, I'll hand over to Gabriel, who will begin with the scaling prediction work.
Thank you, Dan. Let me just share my screen. And if you can confirm that you see the presentation.
Yes.
Okay. Okay, so following the three research questions that Dan has mentioned, we developed three software components, which you can see in this diagram. We use Chakra to extract real traces collected from real training runs, which are performed on real GPUs. And that will represent our ground truth throughout the experiments that we will show. The three software components are, as Dan said, the scaling predictor, which extrapolates across various world sizes, the synthetic chakra trace generator, which generates traces without executing the training process itself, and finally the temporal predictor, which extrapolates timing across operation sizes. We measure the performance of our three software components by developing and adapting a set of metrics that compare real-world traces with our synthetically generated traces. So starting with the scaling prediction model, a very simple presentation of the problem we are trying to solve in its simplest form. We have an example here where we start from a training job that has been run on a number of nodes, in this simple example on 2 nodes. And you can see on the left-hand side that by using the Chakra tools, we can obtain information about execution traces, model parameters, runtimes, and a lot of different information about the training process. So the question we're trying to answer here is, how does this training job scale up when running on more nodes? For example, 4, 6, 8, or 16 nodes. And the first experiments we ran here is that we attempted to see if this scaling up is just a simple matter of linear correlation. So if this can be deduced very quickly and very simply by using a linear regression or linear correlation and so on. The conclusion is that no, operational latency does not scale linearly with world size, and we see a visual example here. We have just a primitive, the A10 mol primitive, which defines an element-wise multiplication of 2 tensors. We have on the y-axis the exclusive duration of the operation, and on the x-axis we have the operation size, which is defined by the total number of elements in the matrix. All these are grouped according to the number of ranks in the world size, and we can actually see here different behaviors at different operation sizes with regards to how these scale up when going from 2 to 4 to 8 ranks. So a few words about the metrics we use to measure the performance of our prediction model in this case. So we are interested in measuring the difference between the real-world duration of primitive calls and the duration generated by our system. So we use what we call the E metric, the error metric, and this is computed as the mean absolute percentage error, which you can see in the equation on the left. So for each node, we compute the absolute difference between predicted time and real time and divide that by the real time of the operation. We average this metric across all nodes in order to obtain the final value. We also compute the Emax metric, and this reports the highest error on a node. So it basically reports the worst case node scenario. In order to alleviate the outliers in measuring runtimes, each experiment is repeated 10 times, and the reported metrics, which you will see in the following slide, are aggregated over these 10 runs. Also, our evaluation protocols for this set of experiments covers the use of more than 50 AI models, which are represented by deep neural networks and large language models, which are popular in research or in industry. So our experiments cover various hardware setups. What we had were 3 setups with regards to the GPUs we used. So we had the 2080 Ti, A5000, and a Cloud AWS T4 setup. And we also looked at setups containing 2, 4, 6, 8, and 16 nodes. As you can see in the table of results, we incrementally developed our data set by adding a different number of nodes, by adding hardware setups, and by adding different AI models. The most important takeaway here is that we obtained a final value for the mean prediction error between 9.2 and 11.4%, with an Emax value that measures the worst case node between 25.9 and 31.1%. The final version of our data set shows a result for the E-value of 10.82% and an Emax value of 28.31%. Moving on to the synthetic chakra trace generator. Our long-term goals for this software component was to generate realistic execution traces for PyTorch AI model architectures, to simulate time and performance based measures based on GPU type and the sizes of the operation, which constitute the AI model, to vary the training parallelism mechanism, the input size to the model, and the number of model parameters. We managed to currently validate for distributed data parallel and fully sharded data parallel. And as you saw in the previous set of experiments, we validated for the three GPU setups I previously mentioned. So what is not yet supported is external or custom, or let's call it third-party PyTorch code. Other parallelism strategies are not yet supported, or some sets of untested primitives. So just a simple idea of what the synthetic chakra trace generator does. The core idea can be easily explained by this simple example. So starting from a pure Python code, which implements Torch AI models. And in this example, we are looking at a simple linear fully connected layer, which performs an affine linear transformation to the input. You can see the code on the left-hand side, while on the right side, you can see the same operation translated into a chakra trace, and basically showing the steps for execution as they are interpreted by chakra. So our general goal here would be to create a software system that would be able to analyze each layer without actually executing the complete deep neural network on the physical GPU, generate these operations for multiple ranks, and finally produce chakra format execution traces starting directly from the model code. So as I mentioned, the processing pipeline starts from the Python code directly. This Python code should be implementing AI models using Torch and Nickel. And this code is pre-processed either by using an LLM or by implementing a rule-based dictionary approach, which transforms the code into an intermediate dictionary of chakra meaningful operations. In the last step, the synthetic chakra trace generator creates the synthetic traces and the graphs. Our current implementation uses the rule-based approach out of these two pre-processing pre-processing ideas. And LLM-assisted source code analysis may be added, and it may be useful for workloads that cannot be handled by the rule-based parser. An in-depth look at the architecture shows how the model file is read, and only chakra meaningful torch operations are selected from the source code, along with the data size associated with each operation, as well as parameters and settings for the model and for each individual operation. The list of operations is then decoded, generating a new list of chakra primitives that are then linked and saved to a merged chakra file. Looking at the first major component from this software system, we have the model reader, which takes as input the model file and its training settings, and passes it along the pipeline. So the model reader extracts the meaningful code and passes it to the operation extractor. The operation extractor only keeps function calls that are significant for chakra in understanding how the model is being trained, as well as additional information about each extracted operation, mostly operation parameters. So the list of meaningful operations is then passed to the node factory, which based on the type of operation that is being processed, parses the parameters and transforms each operation into a set of primitives using a predefined dictionary that defines how operations translate to chakra primitives. The decorator part here decorates all the primitives in a JSON format that allows them to be correctly interpreted by chakra. The node linker establishes the links between the individual nodes in the chakra graph and updates the input and the output shapes that influence the graphs and define the final graph shape. So our experimental evaluation in this case must, of course, be steered towards comparing the shape of the synthetic graph with the shape of the real-world graphs. So the metrics we proposed for these experiments are graph similarity measures. And in this case, we chose the Zhang-Shasha tree-edit distance. So this metric can process tree-like and graph-like structure from a topological standpoint. It does this by checking the number and identity of nodes. It checks all the connections between nodes, and it checks the identity of the nodes based on the node names. So basically on the primitives that are being called. We used here the same training testing setup with regards to GPU and AI models as the scaling prediction model. And our results are computed and reported across 180 evaluated trace pairs. So the generated graphs achieve the ZSS distance of 0 for topology and node labels, meaning there is an identity an exact identity between synthetic graphs and real-world graphs. The final component here is the temporal prediction model. And for this, we start from the following research problem. The current implementation of our system does not yet accurately predict timing information for previously unseen operation sizes, even when measurements are available for the GPU architecture we're trying to simulate. So what we must do in this case is create a framework that will allow us to measure and annotate GPU performance, and which in turn may allow us to extend the experiments to additional new GPU architectures. For the methodology here, we used again the same hardware setup. And just like before, each experiment is being run 10 times, and the duration are averaged over all these runs. And again, just like before, we perform these experiments over with over 50 AI models. We will show the results for 32 primitives with the initial goal of having errors under or around 10%. As this would indicate a low enough variability between our results and real-world samples, and they would allow us to correctly predict timing information. We also propose to perform an analysis of each operation and primitive in order to detect any interesting particularities that may be reported. And looking at the results, this figure shows the error values we recorded with our experiments. Results here show errors between 3.01% and 9.14% for the 32 studied primitives. And as I mentioned before, this indicates a low enough variability that would allow us to correctly predict timing information. Moving on to the analysis of some interesting primitive results. Here we are looking at how the duration of primitives scale based on the size of the mathematical operation they perform. We have on the y-axis for both figures the size of the operation, and on the x-axis we see the duration of the operations. A regression is performed for each of these two sets of values. You can see the trend line in the figures, as well as the R-squared coefficient of determination for the trend line for the regression. So on the left side, we see the A10 matmul matrix multiplication primitive. Here, the size of the operation is defined by by 3 parameters, defining the 3 dimensions of the matrices being multiplied. Here we can see that a simple linear regression is enough to predict the duration of this matrix multiplication primitive. While on the right side, we see the 2D convolutional primitive. Here, its size is more complex to define. As you know, the convolutional operation is defined by the size of the input, the size of the convolutional layer, its filters itself, as well as other parameters such as the number of filters, padding, striding, and so on. This time we see that we need a polynomial regression in order to predict a trend line for these values, and the R-square value this time is around 0.9. So what we demonstrated through this experiment can be summarized by the following. For the scaling prediction, we managed to score mean error across the reported experiments between 9.2 and 11.4. For the synthetic chakra trace generation, we achieved zero topology distance across the evaluated trace pairs. And finally, for the temporal calibration, we have primitive level errors reported between 3.01 and 9.14 for the studied operation size ranges. So this concludes our presentation.
Let's give a big thanks to both of them.
Thank you.
Any quick questions? I have a question. So in this prediction, is it dependent on the CPU type, GPU type, or it is independent?
It's dependent on the GPU type, not on the CPU type.
Okay.
CPU is not something we looked at to vary between experiments.
Okay. And then these final numbers you showed, these are on what kind of GPUs? It's like a NVIDIA's.
They're aggregated. Yes, so they are aggregated across the three setups we mentioned. So we had the 2080 Ti, the A5000, and the AWS-T4.
Okay. Any other questions from online attendees or in person? Yes. Go ahead. Yeah.
Thank you for the talk. Are the predictions mainly based on execution times alone, or other resource utilizations like memory and stuff like that?
They are looking at execution times alone. But of course, the memory and so on comes as a factor. But what we wanted to look at primarily were the execution times.
Okay, thank you.
Any other questions? Okay, so if not, let's again thank both Dan and Mihai.